Okay, guys, everyone, good morning. Just a quick reminder, this is the 5th meeting, so we should have one more at least, and if it's not 2 more, we will see. So we have some announcement to make next week. However, this is the 5th meeting. Now, just a quick reminder, guys, all the past meetings recording has been posted online, so you all can always go to the website stormingrobots.com. I'm going to share the screen really quickly, make sure everybody knows where to go to. All right, so make sure you go to stormingrobots.com, and then at the bottom you see this robotic simulation group. You click on that, and you see all the verbiage in here. And make sure, again, do sign this up at the RCJ site, because as soon as they have any announcement for their competition, you will for sure get the notification. So you do sign yourself up if you haven't done so. And all the past meetings recording, they are posted already. And we even have the samples. So I will continuously update the samples on this site as well. So do keep a note and write down the website name, okay? And today's the topic is, like what I said, Jeffrey and Victor will talk to you about the topic, okay? So as we said, we have one more next week, and then this week is pending. So we need to do some coordination with the LCJ group in order to decide exactly what we may do or may not do this week, okay? So very good. So I'm going to hand it over to Jeffrey and Victor. Oh, I'm sorry. One thing, guys, if you post questions, please post it to moderator. Okay, thank you. All right, go ahead, guys. Take over.
All right, hello, guys. So in this video, we're going to talk about mapping, and this meeting is part 1 of 2 videos where we're going to give you an example algorithm as to how to navigate the maze. Now, if you have ideas on how you want to code your code for navigating the maze, then by all means go ahead. This is just an example. If you don't really have a good place to start, you can listen in to what we say, but like if you don't follow along with everything, that's perfectly fine. You can always use your own method of navigating around the maze. So with that being said, yeah, so we're going to talk about mapping today. Let me share my screen. So basically what mapping is, it's just like mapping in real life. Our robot is going to go around the maze, and as it learns stuff, like where the walls are, it's just going to write that down in some kind of map. That way, if we ever have to go back to somewhere that we already have been, we already know the wall arrangements in that area. So for example, if our robot goes here and travels this entire room, and then it goes here, and then needs to get from this room all the way back to this room, it already has been to this entire room right here. So it already knows the wall arrangement, and we can use an algorithm that we'll talk about next week. We can use an algorithm to find the best path to get from here to here, instead of doing like all sorts of loops and whatnot. You can find the most direct path possible. So that's just basically what mapping is. You go around and you store the wall arrangements of the maze that you have seen. Now, we really need mapping for 2 main reasons. First off, mapping allows us to remember where we have been and where we have not been. That way, we can always guarantee that we traverse the entire maze, because that's just when we run out of places that we have not been. If you're doing something like wall tracing, where you just follow the right wall, or you just randomly move around, there's no real guarantee that you traverse the entire maze, right? Because if you're wall tracing and just follow this inside wall, there could be plenty of humans right in the middle that you miss out on, that are outside the scope of your camera. So you need an algorithm to let you traverse the entire maze and guarantee that you traverse the entire maze every single run. And that's what our algorithm lets you do. It guarantees you that you will always traverse every area of the maze. And the second main reason why we need mapping is what I said before. We can store the wall arrangement of the maze that we have seen so far. That way we can travel the maze, we can navigate the maze efficiently and make sure we don't run out of time. So I'm just going to, okay, so our map, as I said before, needs to do two things. First off, it needs to remember where we have been and remember where we have not been. And it also needs to store the walls. Well, the question is, how do we do that? First things first, we can start off by taking this entire maze and dividing it into a whole bunch of grids. Now, each grid that you see in front of you, we're going to call it a section or a tile. For our purposes, section and tile are synonymous. So this right here would be one tile. This right here would be another tile. This right here would be another tile, and so on. And each one we could also call section, a section at times. But basically, our entire grid, our entire maze is divided into these grids. And our map is simply going to be a collection of a whole bunch of grids. So our map has to be some kind of data structure where it has a bunch of elements, and each element of the map corresponds to a specific section of this, to a specific section of the maze. And yeah, each element is going to store information about this particular tile, such as the walls and have I been there, but we'll get to that later. So I'm going to pause real quick. If you have any questions as to what I just said, make sure you send something to Miss Elizabeth. So just keep in mind that I have my entire maze and I divide it into a bunch of grids, and then each one is called a tile or a section. Okay, next up, we're going to take this grid and we're going to put it on a smaller scale. Now in real life, not real life, but when you code it, your map would have to be the same size as the grid, as this grid. So it would have the same number of rows and the same number of columns. But this is smaller, so it's easier to look at, but it conveys the same idea. It is a collection of a whole bunch of grids, and each grid corresponds to a grid here in the maze. So what we're going to do is we can actually number each of the grids. So we start at the top left, go 0, 1, 2, 3, 4, and etc. And since we find out that, hey, this is just a contiguous segment of, or a contiguous series of numbered tiles, we can actually put this in row form. And as you can see, this representation up here looks like a two-dimensional array, and this row right here looks like a one-dimensional array. And basically, these are going to be our maps. So you can either implement your map using a two-dimensional array, or you can use a one-dimensional array to represent your map. So for this video, we're going to be looking at a two-dimensional array because it's a little more intuitive, but there are drawbacks and benefits to both of the types of arrays. Because, for example, in a one-dimensional array, you only have to keep track of one variable as to which element you're looking at. But anyways, so we now established that we're going to have some kind of array. In this case, we're going to have a two-dimensional array as our map. And each element of my array is going to correspond to a section of my maze. So you can see that element 0 right here can correspond with section 0 of the maze. And then likewise, element 1 of my array can correspond with section 1 of the maze, and etc. And now, since it's an array, each one of these elements can hold values. So the value that is stored in this element can tell us information about the particular section. So let me give you an example. So as I said before, each one of these is a tile. This right here is tile 8. So this right here is a zoomed in version of the big maze we had in the previous slide. And then if we add back the gridded lines as we did in the previous slide, it'll look something like this. Remember, we're zoomed in. I'm going to take out the extra grid lines, and I'm just going to focus on this tile in the middle. So this tile right here. So let's say tile 8 looks something like this. So this section in the maze is stored in element 8 of our array. Now, this tile, it has a lot of information. We're going to call them attributes. So each tile has certain attributes or information about that particular tile. For example, where are the walls and have I visited it before? Now, you can see for this tile, there's a wall to the north, wall to the west, and wall to the south, but no wall to the east. And we have to remember that, assuming when a robot visits this tile, it's got to write that wall arrangement down. And then when it's been here, it's got to mark this tile as visited so that it remembers that I've been here, so I don't have to go there again. So how are we really going to do this? Each element of the array, as I said before, corresponds with a specific section of the maze. And each element of the array, each element of my map, is just going to be represented by 1 byte. So looks something like this. This is just an empty byte set to all zeros. And each one of these bits is going to correspond with a particular piece of information. So something like this. So this first bit is going to represent the north wall. For example, if there is no north wall in that tile, then this bit is going to be set to 0. If there is a wall in the tile, then we can set this bit to 1. This similarly corresponds to the east wall. If there is no east wall, we're going to set this bit to 0. If there is an east wall, then we're going to set it to 1. Then same thing with the south wall and the west wall. And then this right here is the visited bit. It basically represents, have I visited this tile or not? So if I have been there, it's going to be set to 0. So all tiles are going to be set to 0 by default. But as we navigate around the maze, we can start setting tiles, their visited bit to 1 if we have been there. So just a little recap of what I said. Remember, if you have any questions, make sure you send them to Miss Elizabeth, who's the moderator. So in summary, we have a maze, something like this, and our robot starts right here. And at the beginning, our robot knows nothing about the maze. But as it moves around from tile to tile, it can write information that it learns about the maze into the map. So for this tile, the robot is going to be inside of here. It's going to learn that, hey, there are no walls in this tile. So it's going to mark this tile as visited, move forward, and then it's going to be like, hey, there's no walls here. So I'm going to not change the walls, but I'm going to mark this tile as visited. Then it continues. Up here, it's going to say, hey, there is a wall up here, and then etc. So our map is represented by a 2-dimensional array, where each element of our array corresponds to a section of the maze. So element 0 right here of our array, which again is our map, element 0 is going to correspond with section 0. So any information about section 0 will be stored in element 0. And then same thing with section 1 and element 1. Then,
excuse me, I'm sorry, Jarvi. One fellow asked a question. I think that would be good that you kind of explain that, because I think he didn't quite understand what the other bits for. So he maybe, yeah.
Okay, so yeah, back in over here, we only use 5 bits because right now our basic goal is to store the wall the wall arrangement of that tile and have we been there or not. Otherwise, we really don't need any information. So these 3 bits right here are pretty much left alone. While you're coding your implementation, you might find a reason that you need some of these bits. So you could definitely go ahead and assign one of these bits to something else. But for right now, for basic navigation, all we need are these 5 bits. So these 3 bits really don't do anything. But for example, let's say you picked up a human in some tile and you wanted to mark that you picked up human in that tile. You could assign this bit to is there a victim in that tile, yes or no. So something like that. But for right now, these 3 bits, we really don't care that much about. So I hope that explained it. Okay, anyways, we're going back. So once again, in summary, this right here is a tile. And let's say this tile corresponds to this tile. Then we're going to have to store information about this tile inside our map array. So we're going to index our map array with the corresponding section. So let's say this is section 23. So 23 would go inside of here. Then this element right here is going to look something like this. Remember, you could make map a character array, and that would automatically give you 1 byte. So the element 23 of the map looks something like this, and then we're going to have to fill it out accordingly with each bit corresponding with a particular piece of information about that tile. Then, I actually didn't mention this earlier, but we're going to have to keep track of 2 variables. One is called the section variable, and one's called the orientation variable. The section variable is pretty simple. It's just going to keep track of which section of the maze we're in. So if we're in like section 17, our robot's right here, then section is going to be set equal to 17. And as we move around the maze, so if you go up, you're going to have to update the section variable accordingly every time you move. Now, the orientation variable is just going to store what direction we're facing. So north, east, south, or west. Now, you can't exactly store north, east, south, or west, but there are plenty of ways to get around it. You could correspond them with numbers. So north is 0, east is 1, south is 2, and west is 3, and then simply store the corresponding number to the orientation. So if we're in 17, we're facing up, you could just store 0 in here for north. So yeah, section is going to write down which section of the maze we're in, and orientation is just going to write down what direction we're facing. So let me give you a sample. So our robot is in section 23 right here, and it's facing north. Well, we'd fill out our section variable equals 23, orientation equals north, character is another way to do it. Then, since we're in section 23, we have to fill out the information that we learned about section 23. So we're going to index our map at element 23 because element 23 corresponds with section 23. And then we're going to fill out the information accordingly. So we see that there's a north wall, west wall, south wall, but no east wall. So we fill this out. So 1 for north wall because there is a north wall, 0 for east because there is no east wall, 1 for south, and 1 for west. Then, since we're already in this tile, we're just going to mark down that I have been in this tile by setting this bit to 1. And that's basically the overall gist of mapping, of basic mapping at least, for the Erebus competition. So we're going to take like 30 seconds, take the information in, and then go ahead and send the moderator any questions that you have. I know it was kind of a good bit of information.
Okay, as far as I know, half of these people here, since I don't recognize half of the people's name in here, so I'm not sure whether they know what bits really is or bit operation. So that's why I posted and say just tell me yes or no about bitwise operation.
Oh, we don't need bitwise operations. We have a way around that.
Well,
well, yeah.
It's gonna be rough.
Well, all you really have to know is that each element stores 8 bits, and a bit is just a 0 or 1. So this right here is a bit. This right here is a bit, and then we can flip them on by setting it to 1, or we can flip them off by setting it to 0.
Well, maybe we'll add on the topic, talk about bitwise operations later. So maybe just for now, you guys have to, for those who are not sure understanding how bit operation works, just take the word for it. Just yes or no. Yes is a 1, no is a 0. Look at it that way. Okay, and then perhaps we'll add a session later to talk about bitwise operation with these folks. Okay, all right. Okay, yeah, go ahead. I'm sorry.
All right. Otherwise, if you guys have finished any of your questions, I'm gonna hand it over to Victor.
Okay, so as Jeffrey said, we want to use mapping and navigation in order to traverse the maze in, first of all, minimal time, as in we don't have to often revisit unvisited grids. Plus, we want to visit every single grid so we don't miss any victims. So since Jeffrey talked about the ideas, I'm going to walk you through a very basic implementation of what he said. And we're going to do that through a sample. So I'm going to share screen. Okay. So first, let's talk about the tile data structure Jeffrey was talking about. So we're going to implement this in C++ as we've used in the previous tutorials. And we're going to use something called a struct. And if you use C or C++, you may or may not have used structs before. Pretty much, structs allow you to create a user-defined data structure. And structs pretty much contain other variables inside of them. And that's like a basic way to think of them. So for instance, on this line, we're simply creating a struct that stores all the information Jeffrey was just talking about, including the north, east, south, and west, as well as the visited or unvisited. So you might not recognize the syntax with bool, viz, and then :1. So this is just like creating a variable called viz. But the reason why we have a :1 is because we want to utilize what Jeffrey was saying before and only have this contained inside of 1 byte in order to save space. So actually, this entire struct is going to take up 1 byte. And the :1 means that this is essentially something called a bit field. Viz is going to take up 1 bit within a Boolean. North is going to take up 1 bit, and so on. So in the end, you take up 5 out of the 8 bits, and the whole thing has to be a minimum of a size of a byte. So it turns out that every tile we create is going to be a byte, and we save space that way because we don't have to create 5 Booleans inside of 1 struct. And each Boolean itself is a byte if we didn't use this bit field technique. So moving on, we have our maze here represented as a 1-dimensional array. And like we said before, you could use either a 1-dimensional or 2-dimensional array. In this case, this is just a 1-dimensional example. And we define these two things, the size as maze length times maze width. And then we have those definitions up here. And we just defined it to be 35. And now that requires an explanation because what we mean by a maze size of 35 is 35 by 35 tiles. But what constitutes like a tile in this Erebus world? That depends because you'll notice that this world is not perfectly split into tiles. Like there's irregular walls and everything. So we have to artificially determine ourselves what we want one tile size to be. And that just depends on what you need and what works well for you. In this case, we arbitrarily defined it to be 1 meter, which is a good size. So one tile, one of these tile structs is going to map to 1 meter inside of this real simulation world. And assuming that we're mapping it to 1 meter, then a good size for our maze array is going to be a 35 by 35 array. And you want the size to be big enough where your robot never has a chance of going out of bounds in your own maze, because that would be really bad. So you never want to go out of bounds. So just have a large enough array where that's never going to happen. And that's why we defined it by 35 by 35. And moving on, I have my section variable like Jeffrey was talking about, as well as how we're going to store our orientation is with an enum. And we've used enums in the past in our like box challenge tutorial. You might have seen this before. Pretty much, north is mapped as 0, east is 1, south is 2, and west is 3. And then we just create a enum called orientation that's going to store that. All right. This is going to require some explanation. And if you're heavily advanced in C++, you might have seen this before, but I'm guessing that most of you have not. This is something called a C++ operator overload. And this is pretty specific to C++. You might not find it in other languages. What an operator overload allows you to do is it allows you to assign special purposes and functions to your normal operators. For instance, the plus sign is an operator you see a lot used to like add numbers, for instance. And everybody knows what a plus sign does. Normally its purpose is just to add, right? But we can also overload operators for our structures as well as for our enums in order to get it to do something special. For instance, if I have orientation plus 1, normally that would add 1 to whatever orientation we are. So for instance, if we're at north and we add 1, then we go to east. And if we're at east, we go to south. But if we add 1 to west, that poses a problem because west is 3. Normally, if we add 1 to west, we want to wrap back to north, but north is 0. So we're essentially doing 3 plus 1, and that actually goes outside of our enum, which poses kind of a problem. So to solve this, we overloaded the operator for the orientation right here and a number. So anything with an orientation plus the plus sign and any kind of number, it's going to use this special function instead of the normal plus operation you'd find normally. And all this function does is it adds the numbers, but we do an additional thing. We mod it by 4. And modding it by 4 ensures that anything above 4 goes back down to 0. So for instance, if we're at west and then we add 1, that goes to 4. And then 4 modded by 4 goes back down to 0. So we've essentially found like kind of a hack to have it wrap around from west to north and north to west without having to do any extreme amount of coding. So this is very useful for that instance. And same thing for the minus sign. We do the same thing where if we go from north to west, like n minus 1, that should go to west. We simply mod by 4, but we also, before we do that, we add 4 to make sure everything's positive, and then we mod by 4 again. So you've probably never seen this before. That's perfectly fine. It's just something kind of useful to save yourself some time. You don't even have to use this. You could just implement checks manually. It's just easy in our opinion. All right, so moving on. Taking a look at these two functions, this function especially. So how we're gonna read in wall information is using our ultrasonic sensors that are on this robot. And you might remember from previous videos that this robot has 16 ultrasonic sensors surrounding the entire robot. But in our video, we only used the frontal 8, which means ultrasonic sensors 0 through 7. And we're going to keep with that just for the sake of consistency, but feel free to use as many as little ultrasonic sensors as you want. So down here, first of all, we create our robot, and then we create our 8 distance sensors. In this get surroundings function, this is essentially the implementation of what Jeffrey was talking about reading in the wall data for your tile. And how it works is pretty easy. If the distance sensor number 4, which in this case is the frontal distance sensor pointing straight forward, if that's greater than 700, and if you watched our distance sensor video, then you'll know that the higher the number gets, the closer you are to a wall up to 1024 or 1023. Then if it's close enough to the wall, we call set wall, and we pass in our orientation. And looking at the set wall function, all it does is it takes in an orientation and it has a switch statement to set the corresponding wall for that current tile to be true, which means, for instance, if we set wall north, then the current tile's north wall gets set to true, which means that it has a north wall. So going back to get surroundings, we also do the same thing for distance sensor 0 and 7. So distance sensor 0 is the left distance sensor. And we do the same thing except slightly different. Instead of set wall orientation, we say set wall orientation -1. And the reason why we say -1 is because, once again, if we subtract 1, that is essentially going 90 degrees to the left in the perspective of the robot. So for instance, if we're robot orientation is east and we see a wall to the robot's left side, left sensor, then we know that wall is on the north side of the map. So therefore, this is why we subtract 1. And same thing for the right side, that's distance sensor 7, we set wall orientation +1. So that's the exact opposite on the other side. Okay, so this was a lot, and probably a lot of you guys have not used the C++ um, ideas before. So if you have any questions, let's take a moment and you can send them to the moderator.
Jeffrey, you got that one question about the overloaded operator?
Yeah, okay. Victor, if you want to keep sharing your screen. So the question was, when we overload the plus sign operator, does it affect all addition? Like if I do 3 plus 5, does it affect that kind of addition? Or is it only between orient and integer addition? And the answer is, it only affects addition between orient and integer addition, because you can see for both of these overload functions, the first parameter is set to an orient, and the second parameter is set to an integer. So it only overloads for those specific data types.
And of course, you could overload it so that you accept different data types as parameters. But for our cases, what was most useful for us was between orient and adding numbers. So I hope that clears up that question. All right, so I am going to move on. And so down here in this demonstration program, it's just some sample. I'm going to set my orientation to north. So we're going to assume that the robot is facing north. And then just to prove to you guys that the tile is currently empty, I'm just going to print it out. And I'm going to repeatedly in this loop get surroundings and repeatedly just print out the north, east, south, west data on the tile. So we can try to run this. Okay, so you notice that currently the north, east, south, west are all set to 0, which means that it starts off as 0 and no tiles are seen in all 4 directions of the robot. If we move the robot, for instance, closer to this wall, then you'll notice that the west wall gets flipped to 1, which means that there's a wall there. And since I'm not clearing this data, it's going to stay persistent, as in this is the west wall is going to stay flipped. That's okay. If I move it to the east side, then you'll notice that it flips the east side as well. And then north, oops, and that's also gets set. And remember that we aren't checking the ultrasonic sensor behind us, so obviously moving it south won't change anything. All right, and just to prove to you guys that the operator overload is doing something, if I set my orientation to west, for instance, and then in here, I literally turn my robot to face west. Oops. There we go. All right. So now the robot is facing west in the simulation, and I manually set it, the orientation, to west in order to reflect that. So what should happen is, even though I'm facing west, if I see walls around here, then it should still correspondingly map it properly to the right location inside of our data structure. So if I build this, and I run that, so once again, there's no walls originally. If I move it forward, it still sets the west wall, even though we're facing forward since we know our robot's orientation is west. And that means we're going to set wall right in front of us for the west side. But if I move north, then eventually it still works. Despite knowing in our code that we're doing west +1, our operator overload has to work because it goes back to north, which is 0. And then I could also go down here for south. And then once again, we don't have a sensor behind of us, so we can't see the east wall. But I hope that demonstrates to you some of these preliminary mapping steps you have to take. And right now, we're not going to do any movement. We're only worried about mapping because in the next video, we're going to combine this idea of the mapping as well as our navigation algorithm. And it's essentially going to be moving while mapping at the same time. So every time the robot moves into a new tile, it's going to map the surrounding tiles and then calculate through our navigation algorithm what's the closest unvisited tile that we should go to and how to get there. So next week, you'll see this code integrated with the rest of our code. And hopefully by then, this might look like random bits and pieces scattered about right now, but by next week, this should all come together. So if you guys have any more questions, that's pretty much the end of it. So message the moderator because we know this was a lot of information.
Yes, Victor, I just sent something over to the chat.
Okay. Why are humans added to the world only after you click play? Okay, so that's a question regarding Airbus, and this requires some explanation. You may or may not actually be interested in hearing it. So how the humans are generated. The humans are generated randomly by a script, and that script runs when the world simulation starts by pressing this button. So when you press this button, you'll notice that it starts these scripts. And one of
Victor,
the
you're not sharing your screen, by the way.
oh, okay, sorry.
Nope. Okay. Sorry.
My bad. So all I did was I pressed this button, and you might notice this blue text. This is the world information, and you'll notice that it says Object Placement Supervisor, starting controller. This Object Placement Supervisor is the script responsible for placing all the game objects within the world randomly, and this script starts only when you press this button. So that's the reason why the objects are only generated when you actually start running the simulation instead of having them. You'll notice the empty world right here. So I hope that answers your question. And we have additional question. What if you change the orientation to W, but keep the robot still facing north? All right, so that's a good question. Your orientation within the code, which is your orientation variable, does not actually have to be the true world orientation. The only thing that's important is if you keep it consistent, because if you're because even then you don't even know which way your robot's going to start off facing, right? So the only thing that matters is if your orientation of your robot is kept consistent within itself, because it's just relative to what the robot sees. Okay. Anything else?
Does anyone here would like to listen to the more explanation on bitwise operation? If you do, raise your hand. So we get an idea what whether, because we probably can spend 5 more minutes on this.
Okay, you have 2 hands though.
2 hands.
3. All right. Go ahead.
Yeah, I think it would be good if you talk about that. And also before you do that, I mean, just quick thing about the samples you just posted online as well. So remind them then what they are and what they can look at as well. But we got 3 hands, 4 now, and 5. So go ahead. Yeah, talk about bitwise operation. For those who have known very well bitwise operation, it only takes about like probably 5 minutes. Okay. Yeah, go ahead.
I guess I can take care of it.
Yeah, sure.
So,
Make sure they know what bits are first though. 1 by 8 bit.
okay, yeah. So if I, hold on, share my screen. Okay, so, where to start? So when you store numbers, when you store numbers in a variable using code, the computer has to store it somewhere, right? And has to store it in some kind of form that it can recognize. And when you see all the stereotypes about, computer science and whatnot, you always see code in the form of like 0 and 1, a bunch of 0 and 1s, and those are called bits and bytes. So basically they're in binary form, which basically means that, so when we have numbers in everyday life, like 972, those are in base 10. What that basically means is each digit only goes from 0 to 9. That's why it's called base 10. And then when we use binary, that's what the computer uses. It's base 2. So each digit can only store a 0 or 1. And each digit is what we call a bit. So if I make this bigger. So right here we have what's called a byte. A byte is 8 bits, and each one of these digits is a bit. So each bit is either 0 or 1, because that's just the convention of binary. Each digit can only be 0 or 1. And then if we take 8 bits and string them together, we get what's called a byte. And now bytes are kind of like a standard unit that is used for size of variables. So for example, a character, when you go to represent a character, it uses 1 whole byte to store the information. When you go to store an integer, it uses 4 of these bytes to store the information, to store your number basically. So it would take 4 of these, string them together, and that entire thing would be a base 2 number that you're trying to store. And then, so yeah, each one of these is a bit, and that's the most important part. So as Victor said, each one of our tiles is represented by 1 byte right here. So this right here is 1 byte, like I said before, and then each one has specific properties attributed to it. And basically, we have to manipulate this byte so that you can change each bit willingly as you want. Because if you treat this as a regular number, you can't exactly perform addition so that it always modifies this as you want, at least not really intuitively. So basically what we did is we created a structure, a tile structure, so that it's made up of 5 main bits. Then when you go and access the tile, so let's say I do my map, and then I index 23, and then I do .north. This right here accesses the north bit of my map, right? Because remember, index 23 is an element of my map, and an element of my map represents a section. So this right here just represents a section, and then this right here, .n, just accesses the this north bit right here. So if I set this equal to 1, then this just gets flipped to 1. And then same thing, I can flip this to, I can use east, and then that'll just flip this to 1. And then I can do north and change it back to 0. And now this is only because we implemented our tile using a bit field in a structure. If you just had a regular character, let's say I have a character ch, this would also be represented by 1 byte, so 8 bits. Then you can't do your .n or whatever because ch is not a tile structure, and tile creates a bit field, so we're able to do this. For this, you would have to use bitwise and or bitwise or. So I would have to do ch equals ch or 1. So I'm not going to go into very detailed about how or and works, but if I do or 1, then it'll set this 1 bit to 1. And then since the way binary works is each one goes up by a power of 2, if I or it by 2, yeah, then it'll set this next one. And if I or it by 4, then it'll set this next one, and etc. But if you go with the bit field implementation of implementation of the tile structure, then you shouldn't have to worry about these. And then, yeah. So I guess that's the basics. Yeah, so Ms. Elizabeth put a link in the chat, and you can go there for information on bitwise operators. But once again, for this Airbus challenge, if you want to go ahead and use this structure, you shouldn't really have to use any bitwise operators like or and.
Okay. Maybe going forward, the next time you demo that, it might be good just to do it in the. Sorry, I'm taking over for Elizabeth now because class has started for her. You might want to run that in a in Visual Studio and then actually step through it with the compiler. That way you can kind of see what's going on exactly as you step through the code. PowerPoint's pretty bad to teach that with. Just as a suggestion. Okay. All right. Very good. Anyway, yes, so the person asked that they now understand it much better. So very good. Are there any other questions? You can send it to the moderator. I'm now the moderator. Yes, no, going once, going twice. Okay, Itash. All right. You have a question? Okay. Here, Itash, I'll tell you what, since it's sort of like at the end here, why don't I let you talk? Hold on. Where are you, Itash? Jeffrey. Itash, for some reason, oh, there you are. I couldn't see you. Itash, you are unmuted. Go ahead.
Yeah, it wasn't letting me copy and paste it again and like type it again in the chat.
Yeah, chat's terrible. Yeah, the chat on Zoom for some reason doesn't like copy and paste. So go ahead. What's your question?
Okay, so like I said, what if you OR it by like 3? Instead of like 1, 2, and 4, like can you OR it like do the OR by 3? That'd be great.
Can you OR like 3? Yeah, it's because the binary value of 3 is 1, 0, 1, right? So if
No,
you
it's
binary.
1.
I'm sorry, it's 1, 1, not 1, 0, 1. It's 1, 1, right? So binary, maybe you should show that in a. Yeah, it's 1, 1. So if why don't you show that, Jeffrey?
Okay, Visual Studio.
Yeah, sure.
Alright.
You want me to do it? I mean, I can do it.
I'm pulling it up.
Okay.
Let's see.
You could OR it by 3, but like remember that the point of ORing and ANDing is to set and check bits, right? So like ORing it by 3 would essentially set 2 bits at once because you're ORing it by 1 1. If you want to do that, that's perfectly fine, but usually you want to OR like a specific bit, right? Because you want to set a specific bit.
Yeah, yeah.
Does that cover it?
But like, let's say you want to face northeast or something, then you can order it like 3 or 4.
We have another question. How would you read the bit value in the char? You could do that using AND. So if you guys know how OR and AND works, like AND is true if both bits are true, or like both positions in the bits are true. So if I can set a bit by 1, I can set a bit true by ORing its position, right? But I can also check if that bit is true by ANDing it. So for instance, if I want to check north and I AND by 1, it's going to give true if it's 1, and it's going to give false if it's 0.
Do you want me to just show a demo of that or something? I can do that real fast for you if you'd like.
Sure.
Sure.
He
Okay.
said he's okay. If you
Oh,
want, he said
okay.
he's okay.
Okay. All right. Great. Okay. Anything else? Going once, going twice. All right. All right. Thank you very much, gentlemen. Very good job. Everyone, thank you for coming. We appreciate it. And we will post this video up when Zoom is done with it. And I have to edit it a little bit, so maybe a day or 2. So, all right. Very good. I think we'll end the meeting now. Thank you, Jeffrey. Thank you, Victor. Okay. All righty. Take care.